Okay, so hello everyone, I am Srishi Siddharth. So I am a PhD student associated with the Systems and Control Group at IIT Bombay, and I am also the TA for this course EE90. So let's start the tutorial session. Alright, so in this course and in all other control theory courses, what we look at is the model of a physical system or just a system, and then we design control laws for it. So to begin with, we need a model of a physical system. So a model, so in this sense, can be classified into two types. So one is the model in which only the input-output relationship is given. So for example, the transfer function. So you have a transfer function block. There is an input u and you measure the output y. So this is also a model of the system. And another model is the model which you obtain by formulating the differential equation of the given system, and it uses the parameter of the model. So it's a mathematical model which uses internal parameters. So for example, it could use mass, length, or for an electrical system it could use R, L, C, etc. So an example of this model is the state space model. So this is the model represented by first order differential equations. Right, so let's take an example of a simple electrical circuit to understand what does a state space model of such a circuit look like. Okay, so let me just draw the circuit diagram. So there is a source voltage, so I'm going to name it U. And then there are three capacitors. So this is 1 farad, 2 farads, and 2 farads. So to analyze the system, we need to know the voltages across all the nodes. So let's just say that this is the ground node, this is first node, and this is the second. So we need voltages of node 1 and 2, and we also need these loop currents. So let's say this is I1 and I2. So if we know I1, I2, and let's say the voltages across these are, so this is E1, this is E2, and this is E3. And let's say the voltage across the resistor is represented by 1. So if we know what I1, I2, E1, E2, E3, and Y are, at any given time, these represents what the status of the circuit is. Status of the circuit at time t. That is, they completely describe the system. Right, So let's find out what these quantities are. So to begin with, let's apply KCL at nodes 1 and 2. So let's see, so let's mark down the direction of currents. So the current entering at node 1 is second, so it's going to be d1 by dt plus 2d2 by dt equals 2 times n. So or it would be u minus y over 2. Right, let's this equation 1. Then for the second node, we would have 2 times d2 by dt equals times d3 by dt. Alright, so we have two equations and three unknowns. So we need one more relation to solve the system. So let's apply KVL for this case. So apply KVL in the second loop. So this would give us E1 equals E2 plus E3. So we can substitute E3 as E1 minus E2 here, and then we'll get a system of two equations and two unknowns. Alright. So in addition to this, the voltage across the resistor Y can be written as U minus E1 over 2. So about this, so applying KVL in the first loop then. So this will give us U equals Y plus E1. So this will be Y equals U minus E1. Right. Now we have the voltages and we also need currents in the circuit. So current in the first loop is just going to be Y over 2, and current in the second loop is going to be, let's say it's dE1 by dt or 2 times d2 by dt. So it's going to be 2 times d3 by dt. So we have the equations 1, 2, then we have the equation 3, 4, this is 5 and 6. Okay. So out of these 6 equations, if we just know the values of E1 and E2, you can observe that we know what E3 is. Then we can also find out what the voltage across the resistor is, because we already know what the input is. And if we know Y, then we know the current in the first loop. And if we know E2, then we know I2. So this implies that the set of these two voltages is the minimal set which represents the system completely. Okay. So we give a name to such a set. E1, E2 are the states of the system. So now we know the states of the system. We know what input is. So to get output at time t, what we need to do is from equation 4, if we are taking output across the resistor, then y is simply u minus E1. In case we are taking the output as voltage across, uh, let's see, this is C3. So I'm saying that the circuit remains the same, but now we are taking this as the output. Then we would say that y is equals to E3, or we could say that this, in terms of the states of the system, we will have E1 minus E2. This becomes 1 minus 1, E1 times E2, and there is no dependence on the output. Alright, so like we have the relation between output, the states, and the input of the system, we can also define in this way the evolution of the state. So we would have E1 dot and E2 dot equals to some matrix times E1, E2, and then the relation with the input U. So let's go back to equations 1 and 2. So we know what the output is Y. So you can substitute for that. And we also know what E3 is in terms of E1 and E2. So this is E1 minus E2. And for the case when we're taking the output as voltage across the resistor, we have U minus E1. So if you substitute these in equation 1 and 2, you get differential equations for E1 and E2. So I will just write those down directly. So we would have d1 by dt is minus 1 by 4 E1 plus 1 by 4 U, and d2 by dt would be minus 1 over 8 times E1 plus 1 by 8 times U. So we can just substitute these equations in a vector matrix form. So let's just write this down. Minus 1 by 4, 0, minus 1 by 8, 0, 1 by 4, and 1 by 8. So we call this as the system matrix A, this as the input matrix B, this as the output matrix C, and this is a coupling matrix D. In this case, this is 0. So I hope this example was clear to you. So after this, recall from the lectures that after defining what a state space model is, so we have the state space model. So this state space analysis is applicable for linear time invariant systems, linear time varying systems, and then you saw in the lecture that we can actually give some special forms of these A, B, C, and D matrices. That was controllable canonical forms, observable canonical form, and some more canonical forms. And you will see later in the course why these forms are needed. So apart from the state space model, as we have seen in the introductory part, the system can also be defined as some differential equation. So this one gives the first order differential equation. This could be a higher order differential equation. And we would consider some linear differential equation in this course. And another way that we could represent the system is through transfer functions. And these transfer functions for our case could be proper or strictly proper. Alright. So we first talk about what these forms are. These have been done in the first week lecture videos. So let's see what the CCF form is. So there are various names for it. One of them is phase variable canonical form. So I can write this as PVCF. Another name, as you just saw, is controllable canonical form, or CCF, and another name is the first companion. Alright, so let's start with the differential equation of the system. So for an nth order system, we have this differential equation which relates output and input of the system. So we have the nth order derivative of y with respect to t with coefficient 1. So this is in the standard form, that the coefficient of the highest order derivative of the output should be 1. And if it's not, you can just divide the whole equation by this coefficient. Then we have a n minus 1 dn minus 1 pi dt n minus 1. So this is until a1 dy by dt plus a0 by. Let's just say that on the right hand side, we just have some function f of t or u of t. So there are no derivatives of the input as of now. So what we need to do is we wish to express this as the first order differential equations or in the state space model. So we wish to describe this as the nth order differential equations, nth order first order differential equations. So for the controllable canonical form, if this is the given differential equation, then the A matrix is simply the chain of integrators. So 0, 1, all 0, 0, 0, 1. So you can see that 1 is shifting to the right. It keeps on shifting to the right up to the second last row of the A matrix. This is all 0. And the last row of the A matrix is the negative of all coefficient starting from the right hand side. So this would be minus a0, minus a1, minus an minus 2, minus an minus 1. So this is a square matrix n by n. The B matrix, the B vector actually in the CCF form would be all zeros and 1 at the end. So the input is only included in the last row. So this is an n by 1 vector. Then the main point of the CCF form is that we take the output as the first variable. So in this case, C is just going to be 1 and then 0 slot. So this is a 1 by n row vector, and we assume that there is no coupling between the output and input. So these are for the CCF form given this differential equation. Okay. So let's do a question here. So the differential equation is given to be, it's a third order differential equation. We have 5 is for y dt square function of t. So just check first that this is in the standard form. So the question is, give the CCF form of the above equation. So we have just seen how to do this. So A is going to be a 3 by 3 square matrix, and it's going to be like 0, 0 and 1. And then we start from here. So it's going to be -2, -1 and -5. B for CCF is going to be 0, 0, 1. C is going to be 1, 0, 0, and D is going to be 0. So just to recall, the main point of CCF is that output is the first state. So x1 equals y, then x1 dot, which is equal to x2 is y dot. Then we have x2 dot, which is y double dot is x3, and then we have x3 dot. So the differential equation looks like x3 dot plus, let's see, 5x3, okay. Then we have plus x2 plus 2x1 equals u. And if we just transfer these to the right hand side, we get the last row of the A matrix. Alright. So the next form that was discussed in the lectures was the observable canonical form. Also known as OCF, or the second companion form. So there is a relation between the observable canonical form and the controllable canonical form. So let's see that. This is 2. So we have 3 options. So first one is the A matrix for the CCF form is the transpose of the one obtained in the OCF form. Then BOCF is, sorry, BCCF is BOCF transpose, and CCF is COCF transpose. Then we have B, which is ACCF equals OCF transpose, BCCF equals BOCF, CCF equals COCF. And then we have the third option. So we need to select the correct relation between the two forms. So the correct one out of these 3 is this one. Just a second. Yeah. Okay. So, or in other words, if we have just obtained the CCF form, then the way to obtain OCF form is just transpose of the A matrix. Then BOCF is going to be, instead of a column vector now it's going to be a row vector, and it's going to be the one for the CCF form. So let's see. Sorry about that. So it's still going to be a column vector, and it's going to be transposed of the CCF form of C vector, and then we would have COCF would be VCCF transpose. So let's apply it to the question that we have just seen. So AOCF is going to be the transpose of this. So 0 1 0 0 0 1, and then the last one -2 -1 -5. BOCF is going to be obtained from the C vector, which is going to be 1 0 0. Sorry, yeah, 1 0 0, and COCF COCF is going to be 0 0 1. So I hope this relation was clear to you. Now let's move on to the next topic. Alright, so we have seen that if we have differential equation of nth order, then how can we obtain the system of first order inequation or the state space model. Now let's see how we can convert a transfer function to the state space model. So let's see conversion of transfer functions. To canonical state space models. Alright. So if we already have a transfer function, then why do we need a state variable approach? So let's see, there are two reasons for it. So at least two reasons. So one of them is, one of the reasons for transfer function to state variable approach is because there are some control design techniques which have been specially designed for the state variable analysis. So even if we have obtained the transfer function from the experimental data, we need to convert it to state variable form so that we can design control loss form. So because there are some control design techniques designed specially for state space analysis. And the other reason for transfer function to the state space approach or the state variable form is that you can see that the transfer functions or the higher order differential equations are of nth order, but the algorithms which we use, for example, if you write an algorithm in MATLAB to solve for a system, then those algorithms require first order equations for simulation purposes and also for validating the control laws that were designed. So now we know the reasons for converting transfer functions and differential equations to state variable forms. So now there are three problems or three questions that we should answer. That given a transfer function, so first one is that is it possible always to convert it to state space model? So the answer is yes. If we have the transfer functions which I just described, so strictly proper or proper transfer functions, we can always convert to state space models. Then since we can convert them to state space model, then is this state space model unique? So we have just defined that there are various ways to write a state variable form. So let me just, yeah. So there are CCF forms, OCF forms, and many more. So the answer is no, there are no unique state space models. There are CCF, OCF, and so on. But given a transfer function, we can obtain a state space model. And then, since there are many techniques, so how do we obtain these forms? So how do we obtain CCF, OCF, and so on? Alright. So what we are going to concentrate is on this part. So for that, let's consider a third order transfer function. So we have the Laplace transform of y output upon the input rs or sometimes u of s. So this is the transfer function g of s. So I'm going to write down a standard transfer function of third order. So b3s cube plus b2s square plus b1s plus b0 upon. So this is the third order transfer function s cube plus a2s square plus a1s plus a. So just note that this is 1 in standard form. And it was also 1 when we were talking about the differential equation. The coefficient of the highest order was 1. Alright. So the CCF form for this, if we have been given a transfer function, we have some x dot equals ax plus bu, and then we would have some ACCF, BCCF, and similarly CCCF and DCCF. So for this third order transfer function, ACCF is going to be, so again it's a chain of indicators 0 1 0 0 0 1, and we take the coefficient starting from the right hand side of the denominator. So we would have minus a0, minus a1, and minus a2, and then as seen in the differential equation state, this would be 0 0 1. Input is present only in the equation of the last state. Then this is CCF. This is going to be, the output is just the first state, so we have 1 0 0, and there is no coupling, so this is 0. So this was the case when only u was present on the right hand side of the differential equation. But from the numerator of the transfer function, you can see that there are some other terms. So it's not just b0 anymore, it's the first derivative of the input, the second derivative of the input, and the third derivative of the input. So in this case, a general form of CCF becomes d0 minus d3a0. So you take these two terms, then b1 minus b3 times a1, and then we have b2 minus b3 times b2. So if b3 is 0, this implies it's a strictly proper transfer function, and therefore we have a simplified version of CCF where it's just the coefficients starting from the right of the numerator of the transfer function. So b0, b1 and b2. Alright. So if this is clear, let's look at a question. So we have the transfer function g of s. This is 3s squared plus 7s plus 15 s cubed plus 7s squared plus 14s plus 8. So before beginning to solve this question, just check if this is in the standard form. So for this case, yes, it's in the standard form. And also observe that this is a strictly proper transfer function. So now we know what the matrices are going to be. CCF is going to be, this is third order system, a 3 by 3 matrix, and then minus 8, minus 14 and minus 7, starting from here. Then BCCF is 0, 0, 1, and since this is a strictly proper transfer function, CCCF is going to be 15, 7 and 3, and then DCCF is just 0. So for a strictly proper transfer function, we have a simplified C vector, and we can now readily obtain the matrices for the observable canonical form. So this is going to be the transpose 0, 1, 0, 0, 0, 1, minus 8, minus 14, minus 7. BCCF is going to be now 15, 7, 3. So this is OCF. This is going to be 0, 0, 1, and D is still 0. So we have obtained both forms of the in the state variable approach of the given transfer function. Alright. Now let's look at the next question.